That's a really provocative thought.
It is, and what's fascinating here is a subtle but important argument. You see, effects like the Casimir effect or the Lamb shift, which we discussed, yes, they can be interpreted as evidence for real vacuum energy, but they always involve material systems, plates, atoms. So it's a little ambiguous. Are we measuring a property of the vacuum itself or a property of how the vacuum interacts with that specific material system? However, observing the cosmological constants, say, through the accelerating expansion of the universe or even precision measurements in the solar system, is a purely classical measurement of gravity. It doesn't involve quantum test bodies in the same way. So the argument goes, if the observed tiny lambda is genuinely due to quantum vacuum energy, then the classical measurement itself couldn't somehow be canceling it out or causing it to be small. This leads to a pretty radical speculation. Perhaps the observation of lambda being almost zero is telling us that maybe there isn't any real gravitating vacuum energy associated with empty space and QFT after all. Or at least that our current understanding, our current QFT formalism is fundamentally incomplete when it comes to gravity.
Wow. Oh, okay, so what does this all mean then? How are physicists actually trying to solve this deepest of mysteries, this staggering disconnect? What are the proposed solutions?
Well, there are many proposed avenues, but it's fair to say there's absolutely no consensus. People are trying lots of things. Some suggest modifying general relativity itself. Maybe the cosmological constant isn't constant, perhaps it changes over time. These are often called quintessence models, where dark energy is some kind of dynamic field rather than just a fixed vacuum energy. Others look toward quantum gravity theories, things like quantum cosmology, speculating about baby universes, or maybe wormholes that could somehow interact in a way that statistically favors lambda being very close to zero in our universe. Supersymmetry, or Theories Y, was a big hope for a while. It postulates a symmetry between fundamental particles, predicting superpartners for each known particle. In perfect SOES-Y, vacuum energy contributions would cancel out exactly. The problem is, we know supersymmetry must be broken in nature. We haven't found any superpartners, so the cancellation wouldn't be exact, leaving a residual energy that's still usually way too big. And string theory, probably our most developed framework trying to unify GR and QFT, also faces this as a major, major hurdle. It often predicts a vast landscape of possible universes, each with different vacuum energies, which leads into other debates.